Constraint-Driven Design with OrCAD, presented by EMA. My name is Janine Flagg. I'm an applications engineer here at EMA, and I will be presenting today's webinar. EMA, a Cadence solutions provider, is a full-service provider of EDA solutions, including software tools and consulting services. The focus of today's webinar is to show how properties entered in OrCAD Capture may be passed to PCB Editor, where they will be used to assist with placement, create net classes and differential pairs, instruct the auto router, or become constraint overrides. We will also cover the reuse of constraints through the use of technology files, the routing of differential pairs and nets with total etch length properties, and design reuse. There are many properties that may be applied to components and nets in OrCAD Capture to affect the printed circuit board layout. First, we'll talk about component properties. Many component properties are part definition properties. However, I'm going to show you a couple useful design-level component properties. The room property is used to help group components together for placement on the printed circuit board. And the hard location property is used to lock reference designators so they cannot be modified by the auto rename program in PCB Editor or the back annotation process. Next, we'll talk about net properties. Some net properties are used to create differential pairs or net classes. Some may become constraint overrides, and others may be used to instruct the auto router. The net physical type and net spacing type properties may be used to create net classes in the physical and spacing domains. Net classes are used to group nets that may require special constraints. The min line width property becomes a constraint override in PCB Editor. The route priority instructs the auto router to prioritize specific nets. A route priority of 1 on a net would instruct the auto router to route that net first. The total etch length property allows the user to specify a minimum, and or a maximum overall net length. Now let's talk about differential pairs. We can auto-assign differential pairs in a design if they are named in a specific way. Here are a few examples of signal naming conventions that will allow them to be auto-assigned. As you can see, it requires that the net names be identical for both members of the pair with only a suffix to differentiate between the positive and negative members. To assign differential pairs in OrCAD Capture, you go to your project manager, select your design, and then select Tools, Create Differential Pair from the top menu. As you can see, you may use the resultant Create Differential Pair form to manually assign differential pairs. However, if your nets are named as described in the last slide, the assignment can be done automatically. Use the Auto Assign program, click on the Auto Setup button, and then in the Auto Setup window, fill in the following parameters. In this example, we want DP underscore added as the prefix to each differential pair name. We will then tell the program to search for the suffixes underscore P and underscore N to identify the positive and negative members of our differential pairs. Once all differential pairs have been identified, we can simply click Create and then close the dialog boxes. You can also set constraint overrides such as differential pair minimum spacing and differential pair maximum uncoupled lengths to create boundaries for your differential pair routing. Once you have added all desired component and net properties in OrCAD Capture schematic, you will want to pass them on to PCB Editor. Properties are passed during the Create Netlist process. So you'll first select your design in the Project Manager, and then select Tools, Create Netlist from the top menu. In the resultant form, you will click on the Create PCB Editor Netlist and Create or Update PCB Editor Board checkboxes. Then you will fill in the input board file name if you have one. An input board file might be a template board file that contains a board outline, layer stack-up, and maybe even some constraints. Next, you will fill in the output board file name as desired. You will need to check your allegro.cfg file to make sure all properties in your design will be passed to PCB Editor. To do this, click on the Setup button and then on the Edit button in the Setup form and add any missing properties to the list. save the allegro.cfg file, and then click OK on the Setup form. Lastly, click OK in the Create Netlist form. Your netlist with properties will be read into your printed circuit board. Once your room properties are passed to the PCB editor, you may define the rooms or areas where you would like each component group to be placed. These rooms may have constraints associated with them. As an example, rooms may be defined on top side only, bottom side only, or both sides of your board. You may assign a room a hard property, which will require all component members to be placed completely within the room and no non-members will be allowed. Or you may also assign a room a soft property, which is treated more as a suggestion rather than an actual constraint. Now you can place your rooms using the Place Manually command, which will filter out all components in the placement list except those belonging in the room specified. Or you may use Quick Place command, which will put the components in the proper rooms, but not in any logical placement. Next, we'll talk about technology files. Technology files allow you to reuse design parameters, design level constraint data, constraint modes, cross-section information, and user-defined properties. Using the Export Tech File command, you can save off a technology file from a completed board. Then, using the Import Tech File command, that information may be read into new similar board files. So once your chosen technology file has been imported, you can assign the constraint sets from it to the proper nets, net classes, and differential pairs that were imported from the schematic. At this time, I'd like to take just a few moments to go over the various differential pair constraints. The minimum line width is the ideal or required line width for the nets included in a differential pair. The primary gap is the ideal edge-to-edge separation between the two members of a pair. The neck width and net gap are the line width and edge-to-edge separation required if the differential pair must enter a tight area, such as a BGA. The plus or minus coupled tolerances are tolerance values that are applied, either added to or subtracted from, the gap values. The minimum line spacing is the line-to-line check that ensures the primary gap minus the negative tolerance does not fall below the minimum line spacing required for your board. The max uncoupled length is the maximum length in database units a differential pair is allowed to remain uncoupled. And the gather control with ignore or include allows the user to specify whether the differential pair length from the component pin to the gather point is factored into the DRC value for uncoupled length. The phase tolerance is the difference in the overall length between the two members of a differential pair. This constraint is available only in Allegro PCB Designer or above. Most of the constraints for differential pairs are actually set in the physical domain of Constraint Manager. There are two reasons for this. One is that the line width and separation constraints really control the physical characteristics of the nets. And the second is because the line width and separation between the two members must be specified on a per layer basis based on the required impedance. Only the uncoupled length, gather control, and phase tolerance are set in the electrical domain. Notice, though, that you can see the constraints set in the physical domain while you're in the electrical domain. Before routing, we need to set up a constraint region around our BGA. This constraint region will have similar line width or smaller line widths and spacing constraints associated with it. This means that when the routes cross the region boundary, they will automatically change to meet the assigned constraint. Once all constraints are assigned to your critical nets, you can start the routing phase of your design. The differential pair constraints control the interactive routing behavior of the pairs, so that when you select a net, that is a member of a differential pair, both members of the pair will be attached to your cursor at the required width and separation. There are several routing options for differential pairs. You can route differential pairs using 90 or 45-degree angle corners, or you can route them with arced bends. You also have access to several different via patterns during routing, such as a vertical, horizontal, diagonal up, or diagonal down configurations. There are two routing styles for differential pairs, edge to edge on the same layer or tandem on adjacent layers. To route tandem styles, you must first seed the routing by starting the routes on the signal layer in single trace mode on the desired layers. Then you can pick up the pair and continue routing. When working with differential pairs, you will see a DRC flag with the initials DU if the uncoupled length exceeds the maximum allowed. You will also notice that the line segments that are in violation have become highlighted, making it very easy to find and correct them. The total etch length constraint is used to specify minimum and or maximum overall length of a net, XNet, differential pair, or all nets in a bus. Either value is optional, so it is possible to specify only a minimum or only maximum length. The delay tune command may be used to add lengths to a net to meet the total etch length constraint. It is possible to match the length of a group of nets using the total etch length constraint by routing the longest of the nets first and then setting the minimum and maximum total etch lengths accordingly. The display constraint command reports the constraint value that was used to resolve the physical constraint on any single selected database object. It can also report the constraint value used to resolve the spacing between two selected objects. The display constraint command can help you see how the tool resolves to a specific DRC value. Last, we'll talk about design reuse with placement replication. Placement replication is available through the placement application mode in OrCAD PCB Designer Professional or above. It allows you to save off component placement, related routing, localized copper pores, and reference designator placement of a particular circuit in a layout. The saved module may be reused within the same design if there are multiple identical channels or in another design that contains the same circuit. So to use the placement replication command, you'll first need to identify and save off the module for the circuit you wish to replicate. Then you may apply that circuit module to the parts that will make up the new circuit or circuits. Once placed, these modules may be rotated, mirrored, modified, and updated. So I'm first going to start out in OrCAD Capture, and I'm going to show a few ways to make it kind of easy to add properties that you need on your components and on your nets. So first, what we want to do is we want to add the room property to all the nets in a particular hierarchical block of our schematic. Okay, it's for the high-speed RAM section. So the easiest way to do that is to go to your project manager, select the hierarchical block, and click Edit Object Properties. Okay, so this brings up all the components that are in that, and actually all the nets too if you needed to do something to them, but all of them that are in that particular room. Okay, so, and we can click on the property that we want to add and click Edit. Okay, then we can simply add what we need, add the value for that room. So we're going to call this the mem room. Okay, and we'll use that later when we're placing our design. Okay, the next thing that we want to do is go in and add the hard location property to J1. Okay, so here's J1. The easiest way to get into the property editor is to simply double-click on the component. Then we can go in and just add the hard location. And we'll just say that it's true. Okay, so we do want it to maintain whatever that location or whatever that reference designator is. Okay. Okay, and next we're going to add a few properties to some of the signals. Okay, so we're going to start out with adding, we want to identify our a particular bus. Okay, so I'm going to go to page 2, and I have this bus VD0 through 7, and I'm just going to select all the nets here. And I only need to select them in one section, and then click Edit Properties. Okay, it brings up all those nets. Let's go to the flat nets, and I'm going to add the net spacing type and net physical type. Okay, so let's go and add net physical type first, and again we'll just select it and click Edit, and I'm going to call this VD underscore nets underscore PH. Okay, and then for our spacing, we will add just VD nets. So we're just, what this is going to do is it's going to create net classes in the physical and spacing domain in the Constraint Manager once we get into PCB Editor. Okay. Next, we're going to add a total etch length to another bus. So let's go back to page 1 of our schematic, and we're going to select D0 through 7. Okay. We're going to Edit Properties again, and we're going to add, let's go to the Flat Nets tab and add the total etch lengths. Okay, so we see total etch length here, and the syntax for this is actually pretty easy. So our minimum length is going to be 2,300 mils, and then we just add a colon and add our maximum, which is 2,400 mils. This gives us a 100 mil window for our min-max total etch length. Okay. And then last, we're going to actually go in and we're going to work with our differential pairs. Okay. So these are the differential pair nets that I've identified. So I could actually select them here and then manually go in and create differential pairs. I can also go to my Constraint Manager and go into Tools, Create Differential Pair, and manually select them and add them here as well. But because they were named in the way they were, with the net names identical with just the suffixes, I can just click Auto Setup. Okay, so I'm going to say I want DP underscore as a prefix to the name of the differential pairs, and then I'm going to add an underscore P for the positive and underscore N for the negative members. And it searched my net list and it found these nets that meet that criteria. Okay, so if there's something in here that shouldn't be, I can actually remove it. Or if everything looks good, I can just simply hit Create. Okay, so if we go down the list now, we can see that we do have some differential pairs created. Okay. Okay, so we can close this window and that window, and then let's go back here, and we actually want to add just a few more, a couple more constraints, or a couple more constraint overrides really to these signals. So let's select them and click Edit Properties, go into our flat nets, where you can see here's our differential pair names that were added. Now I'm going to add a minimum spacing. So my very minimum spacing for these are going to be 4 mils. Okay. And then I'm going to, I also want to control the maximum uncoupled length. I'm going to set the very maximum is going to be 400 mils. Okay. Okay. So we've added all of the constraints that we need to our design, And now what we want to do is go ahead and we'll save our design and pass these constraints over to the PCB editor. And we do this through the create netlist command. I'm going to have an input design. I have one board that's actually partially placed. Okay. And then I'm going to create a new design. I'm just going to call it number 4. Okay. And I'm going to go ahead and excuse me, read in my net list. So first, before I do that, though, I want to go into the setup and make sure that, first of all, I'm pointing to my allegro.cfg, which is in the under my install directory under Tools Capture. And then I want to go in and edit it and just make sure that all the properties I want to pass are here. So as an example, diff pair min space is here, my uncoupled length is here, okay, differential pairs is here, so we need that just to even pass our pairs. Okay, my room property and hard location are here as well. Okay, so let's go ahead and run the net lister. Okay, I want to bring up my design in OrCAD PCB Designer Professional. Okay, and here's my partially placed design. And if we look right now, this does not have a stack-up set, but it does have the information imported from my schematic. So if we go in and look at, I have some total etch length. My total etch length came through. Okay. I have my differential pairs came through and my net classes. Okay. So let's just go ahead and place the rest of the components on the board. And to do that, there's a couple different ways. You can use place manually, and then I want to place by room, and I'm going to do the LED room first. Now you notice once I select that, it actually filters out all the components except those that actually belong in the LED room. Okay, so I'm going to place that and then zoom in to place the rest. There we go. Okay, and I could actually click this one box here, and it would give me one after the other on my cursor automatically, but I actually want to place them in a particular order, so I'm just going to select them from the list myself in the proper order. Okay, so first I want to place the resistors. And then the diodes. Okay. Okay, so the next way that I'm going to show you, an easy way just to kind of get the components in the proper area, is to use the quick place by room. So I can select my memory room, the one we assigned in the schematic, and just go ahead and click place. And it just kind of puts the components in there, but as I said before, not really in necessarily a logical placement. Okay, so this room I would go in and then just tweak. I would move the components around to make the best possible placement. So I'm actually just going to go ahead and open up a design. It has the placement finished, and move on to the routing portion of the demo. The first thing we need to do here, we haven't really added our constraints here. We've added, everything that's come in so far has come in through the net list. So we have our net groups or our net classes, and we've got our differential pairs and so forth, but that's all we have right now. So if we go ahead and look at the constraint manager, as you can see, there's no net classes or no constraint sets have actually been added to the different domains. So let's go ahead and import our technology file. Okay. So I saved off a technology file from a similar design, 6-layer high-speed, called it. And you can have a library of technology files and reuse them many times. And I will just import that into my design. Okay. And now if we go ahead and look at my layer stack up, we can see I have now 6 layers. Okay. And before I forget it, I'm going to go ahead and import a parameters file where I've saved off my color setup. Okay, so I don't have to go in and actually every time change the colors of my layers. My parameters file does that for me. Okay, and then next, let's go into the Constraint Manager and make sure. Now we have, the technology file actually brought in all of our constraint sets, but we need to make sure that things are actually applied properly or assigned. Okay, so we brought one in for differential pairs in our electrical domain. So let's make sure, go ahead and assign that to all of our differential pairs. Okay, then we can go into the physical domain where we've brought in a bunch of other constraint sets. Let's go to our net section. Again, we want to make sure that our differential pairs have the diff pair constraint set. Okay, and you can see this actually comes from the electrical domain, but we can see it while we're in the physical domain, and vice versa. Okay, so our clock net's got a 6 mil line width, and our VD bus actually got an 8 mil. Okay. We also have a region around our BGA, and it got some the BGA constraints. Okay. So next, let's go into our spacing domain. Okay, we got several other constraint sets. So our net classes, clock has an 8 mil space, and VD nets has 6 mil space. We don't have any special spacing for our differential pairs. Okay, we could, but we haven't set them up here. Excuse me. We also have some class to class. So what's going on here is we've said the clock nets get an 8 mil spacing, but between clock nets and our DC nets, net classes, we have to have 15 mil spacing, or between our clock nets and our VD nets, we have 15 mil. Okay, so also between DC nets and clock, and between VD nets and clock. Okay, so we're actually just really missing one. So we've said our we can create one more net class, and to do this, we want the VD nets to our DC nets. Okay, so we need to create one more, and we can specify that between our VD nets and our DC nets need to be 15 mil. Okay, and then again, we have a region specified for our spacing as well. So once we know that everything is assigned, now we can go ahead and do some routing. I'm going to just start routing a couple of traces out of this constraint area around our BGA. Okay. And you'll notice as I route and I cross that boundary, it automatically changes the trace width for me. Okay, so I get like a 4 mil width here, and I get an 8 mil width here outside. Okay. So next I'm going to route my differential pairs. Here's my differential pairs, and there's several different ways to route them, as I mentioned before. So we can route them. As soon as I pick up a member of a differential pair, it gives me both of them on my cursor, right, and at the proper line width and separation. So I'm actually going to go and select, I want to route them with arcs, and I'm going to use 90-degree arcs here. Okay, so you can see as I route them, you can get the actual arc. Okay, and then just bring them in. Oops, 1, 2. There we go. That's a little better. Okay. Once you've placed them, of course, you can also do, sliding or whatever. Okay. So my slide is actually set to 45, but I can also actually slide the the arcs themselves and make them larger. Okay. I can also set up and route, say I want to route with lines, and of course I always want to use 45-degree angles. Okay, let's bring this, actually let's bring this a little bit closer. So I'm just going to route this through here, and then when I route the next one, I'm actually able to go ahead and shove this, okay, and get it to make room for my next pair. Thank you. So, and you can always, like I said before, you can always slide these things too, you know, make them a little bit neater, cleaner, whatever. So, and they do slide as a pair. Now, if you ever want to change something as a single net, you can just right-click and select single net. Okay. So I'm going to move up here, and these ones I'm going to route using, I'm going to pop in some vias. Okay. And you'll notice when I change layers, it automatically changes the line width and the separation for me based on my constraints that I set up in the Constraint Manager. Okay. Okay. So, and you can, you know, you have different via patterns to choose from if you want to. If I wanted to do a diagonal or something like that, I could do that and then continue routing. Okay. Sometimes if you have a tight phase tolerance, though, assuming you have Allegro PCB Designer, you can end up with some phase issues using the diagonal sometimes. It just depends. So there's some differential pair routing. Now this group of nets up here that's the bus where we added the total etch length. So if I go and route this, okay, I'm going to route this and kind of bring it through here, and so you'll notice that I got a DRC marker. Okay. And my DRC marker says it has an EL, so that's for electrical length issue. So that means I need to add more length to my net here. Okay, I'm going to do that by using the delay tune command. And you'll notice when I pick it up how the line is kind of highlighted. There's sort of a dashed line that goes through it. So it has that. As soon as I add enough length to meet my minimum total etch length, the highlighting actually goes away. If I add too much length, the highlighting comes back. So you can see when it's in an unhighlighted or non-highlighted mode, it means that you've met your constraint. Okay? And as you can see, the DRC flag is gone now. Okay, so so the last thing that we want to do is I want to show you, one of the last things. Let's see, I almost forgot. I wanted to just show you real quickly how the constraint, display constraint command works. So if I were to select this one single net here, it shows me the physical constraint that's being used to resolve that net. So it gets an 8 mil line, okay? And that's actually the constraint set name was 8 mil line. Now if I select the trace next to it, it's going to show me the name of the constraint set and the value that it's using to resolve the spacing between the two nets, which is 6 mil space. Okay? So then last, I'm going to show you some design reuse using using the placement replication. Okay, so let's go and look at at this design. So I have this design with a circuit that is completely routed. It's routed with vias and micro vias and blind and buried vias and so forth. And I'm going to replicate this. Okay? So first, I need to make sure that I'm in placement application mode. Okay? Then I'm going to select that and right-click over it and say I want to create. So place, replicate, create command. That's what I'm going to select. And I need to pay attention to my command window down here because it will tell me to select or unselect any additional etch and then click Done. Okay, so it's right-click and do Done. And then it's telling me it needs an origin for this. So I'm going to use this pin right up here on U120. And I want to snap to the pin. So I want the center of the pin is going to be my origin. Okay, and I'm going to call this 4. It's going to be module 4. Okay, so we're done creating our module. Now what we want to do is replicate it. Okay, so first, again, in placement application mode, I want to select all the components here. And there's actually more components than I need, but that's okay. It will only use the ones that it needs to do the replication. And I'm going to say place, replicate, apply, and we're going to use number 4. Okay. And here it brings up a window that allows me to swap components. So because this is actually not looking back at my schematic, it may not understand that certain decoupling capacitors exactly which module they belong in. Okay. So it gives you the opportunity to swap certain components that are swappable. I'm not actually going to do that, so I'm just going to go ahead and hide this window and continue and place my modules. So it's going to just give me one after another on my cursor. One more. Okay. And we'll go ahead and place those. Okay. So next, what we might want to do is we want to kind of align these guys, tidy them up. So I'm just going to say Align Modules. And then over in my Options window, I want to also equally space them. Okay? So as soon as I select that, you see that all the modules are equally spaced and kind of lined up. Okay? Next, I probably want to go in first and set my my super filter. If I turn my super filter on to modules only, then I will only be selecting modules. So this is really a nice application for the super filter. So doing that, now I can go in and I can actually swap the placement of certain modules. So I can swap these guys. Okay. Let's say I want this one swapped with this one, and then maybe this one swapped with that one. Okay, and so that way I've kind of straightened out these the connections into the BGA between the modules. Okay. I can also go in and modify one of the modules and update. Okay, to do that, let's go turn off the super filter temporarily, and we're going to go in and change something about this module, or change a couple things probably. Let's do an edit change and change the line width to 25 mils. Let's kind of puff up this line width here so we can see that we've made a change. And then I'm also going to delete this one shape. Okay, let's delete this one shape. Okay, so now we can go in and update. So to do that, first of all, I need to go in and set my, do it done here, and then set my super filter back to module. And now I can select this module that I've modified and say I want place, replicate, update. Okay. And again, I want to pay attention to my command window because it helps me walk through the process. And it says go ahead and select or unselect any additional etch and click Done. So I do that. It comes up and says, which one do you want to update, or what module do you want? Well, it's number 4 that we've been working with. It exists in our design. Okay, all these other guys reference it. And I do a save, and it updates all of my modules. Okay, so you can see all of them are now missing that shape, and they all have wider traces. Okay, you can also take these guys and you can mirror them and rotate them. So I'm going to rotate it. I'm going to mirror it onto the other side, and everything rotates and mirrors properly. Okay. So that's the end of the demo.